Hello everyone, let's get started. Uh, this is Dr. Suguti here. So in this lecture series, we are going to discuss continuum mechanics. Continuum mechanics, it is one of the fundamental course in civil and mechanical engineering. Uh, the also the continuum mechanics concept, the application of this concept, it's vary from simple experimental approach to the very large scale applications. Even most of the concept in mechanical engineering and structural engineering develop based on this continuum mechanics. In this course, we are going to start with the preliminary level. Then we will move step by step in the advanced level of continuum mechanics. This course will give you the answer for some of the questions you had in your undergraduate courses, especially in strength of materials and solid mechanics. In those courses, you have taken some concept without folk in details in those area. Some of the things you directly taken and just giving like a definition, and you could have moved on from that. But in here, we are going to discuss in details from the basics and in some in-depth discussion regarding this continuum mechanics. Okay. So before moving to the subject, let me give some brief introductions. For example, let's say, let's take one matter, right? One medium. If you go to small enough scale, a body of, let's say, let me take aluminium. Let's take the example of aluminium. Aluminium, right? I think aluminium. Okay. So in this case, if we go into very small scale, that means in not even micro scale, in nanoscale level, you will get the aluminium atoms. These aluminium atoms are combined from the metallic bond between the atoms and form this aluminium metal. So now, even though if we go further and further, then you will end up with this aluminium atom, one aluminium atom. It consists of proton and neutrons. Also, it's surrounded by the electron orbits. So that means, finally, we know the matter is not continuous. But in case of the reality, that means in real life applications, we have the true physical behavior. Then most of the cases we deal with the continuum matter. So that means we don't deal, most of the engineering application, we don't deal into this atomic level scale of the material. So therefore, here in continuum mechanics, the first things we assume our matter is continuum. This is the very first assumption we make. Why we make these assumptions? There are two important reasons. The first reason, in most of the engineering applications, we deal with the problem with large scale. For example, let's say one civil engineering application, buildings, bridges, roads. These everything we deal with the very large scales. If you consider the element level, let's say one wall, one beam, one slab. So these are kind of a large scale objects. So therefore, we no need to worry about these very smaller scales, that means atomic level scales. So in this case, we can assume our matter is as a continuum. This is one reason. The second reason, because we understand the mechanistic behavior of our material through the experimental study. So, in let's say the concrete. In concrete, to study the strength of the concrete, we do cube test. This cube test, we do it in the macro scale level, not even the atomic scale. So therefore, we collect the information, the mechanical behavior of the material with a large, that means macro scale specimen. So in that case, we assume the material is a continuum. The matter is a continuum. So this is the two important reasons. One is physically we deal with the large scale problems. Then also our experimental design, experimental approach for this kind of the physical problem. To understand the material, we collect the experimental data in the large scale level. So therefore, we need to model some mathematical formulation based on physics-based model to validate those experimental data. So in that case, if we assume as continuum as a material as a continuum, that assumption is reasonable for that case. Okay, so now, so let's see that now I gave the explanations. What is the meaning of continuum? So now if you assume your material is a continuum, so that means there is no any discrete the material point inside the matter. So now it's a material is a continuum. So now, according to this assumption, if you go further and further in the small scale level, so now we will end up with some material points. Even that material point is a continuum. Then what is our assumption? These material points, it's uniformly distributed to the entire domain of this matter. So that means this point we also assume as a representative of entire matter. So now why we can assume that? Because the previously we assume our matter is a continuum. That's the very first things. After that, so we can, if you take one point in the material, that point I can consider as a representative of all material. So now if I develop any model for this point, then I can apply the same model for entire structure. So this is the very first things you must understand in the continuum mechanics. Okay. So now we discuss what is the meaning of continuum. So now we will move on to the continuum mechanics. So what is continuum mechanics? Continuum mechanics, it's actually study the material by applying two concepts. One is the kinematics. So another one is the mechanical behavior. Study the material by considering kinematics and mechanical behavior. This study, that means if you apply these two to understand the material behavior, then That approach we called as a continuum mechanics. What is the meaning of kinematics? Kinematics is actually we consider the motion of the objective without considering the forces, without considering force. So that is called kinematics. What is mechanical behavior? Now, material behavior subject to the force now. So with force. Okay. So without force, with force. So finally, we will come up with one general equations. In model mean we consider as a equations. Okay. In this continuum mechanics theme, we develop two type of equations. The first one, it's called fundamental equation. What we mean by fundamental equations? This fundamental equation, it is developed based on the universal laws. This fundamental equations, it's always true regardless of the material, whether it is concrete, steel, aluminum, whatever the material, this fundamental equation is same. How do we develop these fundamental equations? Using some universal law. The first one, we use a balance of mass. That means principle of mass conservation, right? Or I can say it this way, right? Conversion of mass, right? I can say how can I'll write it this way. Yeah, conservation of mass. I'll write, right? Conservation. Or you can say the balance of mass. In one of the equation you studied in your fluid mechanics, this one, right? Q, the flow rate, it's constant, right? Even though if we change the cross section, the same flow is passing through that cross section, right? So you studied like cross sectional into volumes, velocity, something like that. How do we get this equation? Based on this one, right? That means mass not change with the time. Okay. That means derivative of mass with respect to time is zero, right? This mass is constant. So that is the conservation of mass. In some cases, some application, let's say the nuclear physics, there's a loss in mass, right? So in that case, mass is converted as energy. So again, we have to consider that one in those type of application. But here we don't deal with that type of problems here. In general engineering problems, the conservation of mass is still valid. Next one, the second one is principle of momentum. So in the principle of momentums, here the Newton's law come into the picture. That means that principle of momentum must be satisfied. That means F equal ma, there are two type of momentum, linear momentum, angular momentum. Those things must be satisfied. So that means if you apply this equation, conservation of mass, we will end up with one equation. Principle of momentum, again we will end up with another equations. Then third one, the principle of energy through the thermodynamics principle, right? Principle of energy. So here we use energy balance, entropy. So those type of thing we will apply here. So by using these three laws, these are the three fundamental laws, right? Any physics problem, if you develop any physics problem, the fundamental equation for that physics problem, these three must be satisfied. Okay. So by using these three universal law, we develop the fundamental equations. Then the second one, we develop the equations called constitutive equation. Constitutive models or equation, right? Constitutive model equation, right? These constitutive equations, it is now the material specific. It is not the generalized equation. So for example, you will have one constitutive model for steel. You cannot use the same equation to study the behavior of the concrete. So this is the material specific. So here we will take some assumptions. So some of the things you might have studied in your strength of material class, the elasticity model, right? The stress equal Young's modulus into strain. This is general simple elasticity model. This is only you can use for elastic material, right? So you cannot use the same equation for all cases. So this is again the material specific, right? So these are the two equations. Okay. How we define these two equations, especially the first one, the fundamental equation. When you use this fundamental equation is the key, right? So that fundamental equation, to use this fundamental equation, again, we have two approach for fundamental equation development. The first one, that means for fundamental equations, to develop fundamental equation, again, we use two approach. The first one, okay, so I can say this way, right? You consider a finite volume of the matter, then you apply your laws, right? The universal laws to that finite volume. Then you come up with the equations. So for example, in your structural analysis or strength of material class, you might have discussed beam, right? So in the beam, if you want to calculate shear force and bending moment values, that means internal forces in the beam, you consider one finite volume. You have drawn the free body diagram, support reaction, and shear force, bending moment. So this is, you consider the finite volume. Then you draw the free body diagrams, then you apply your universal laws. Right? So in that case, you don't apply the first one and the third one. You apply the principle of momentum, right? Newton's law. You can calculate these forces. Again, here you consider the finite volume. So this is one approach, right? You can consider the whole body. The second one, we use a differential approach. That means field approach. It's called field approach, right? So in this case, we considered very small volume. This is we call infinitesimal volume. So in this case, we consider very small volumes. That volume is, let's say if it is volume, it tends to 0. So we apply some calculus techniques. We use differentiation, integrations, those things. We for infinitesimal element, we apply these equations. Okay. So these are the second one is the most generalized approach. Okay. So this is the what we are going to discuss here, because the first one you have discussed in your the undergraduate class courses, strength of material, those things. That those are the very basic things, right? Very simplified approach. But we are going to discuss these things here. The second part is here. Okay. So this is the overall introductions of the continuum mechanics, what you are going to study here. Then first, we will study these things, the fundamental equations, how we develop fundamental equation. Then we discuss